So, good morning, one and all. Today we have discussed how to find out the degree of static and kinematic redundancy. Now, generally, for static redundancy, we have considered the external and internal. For example, DSi, that is the degree of static redundancy or indeterminacy, is equal to DSi external and DSi internal. Now, for external redundancy, what is the formula? Formula is very simple. The formula is simply we can say R, that is the reaction component, and E is the number of equations available, R minus E. And for internal, generally, if we know the reactions, even though the beam or any structure is indeterminate, it is not possible to find out the uh, forces. But if we know the reactions, then we can find out the shear force, bending moment, and axial force, or we can say that the shear stresses, bending stresses, and axial stresses. And that's why, in specifically in case of beam, it is zero. So internal is zero and external is R minus E. So let us have a few examples. Here we have find out the static redundancy or indeterminacy first. Here the beam is simply supported at one end. So there is one reaction at support, say this is support A, this is support B, and this is the free support C. That's why this is the beam simply supported with the overhang on the right side. So there are two reactions. One is the vertical reaction, that is RA, and second is the horizontal reaction at A. But in case of the beam, we have neglected the axial deformation. This will be not considered. But generally, when we neglect the axial deformation, then HA is equal to 0. But when we have considered the general condition, general case, in that case, there are two reactions at support A and at support B, there is a roller support, and therefore there is only one reaction, that is the perpendicular to the plane, which is say RB. And at free end, no reaction. And that's why when we consider the number of reaction component here, so 1 and 2 at support A and 1 at support B. So it is 3. So for the beam external, it is 3, and equations available is also 3, and that's why we get the 0. So degree of redundancy for this beam is 0. Now the question is, when we neglect the axial deformation, we can consider only two vertical reaction, and this will be not considered. That means the HA is considered as 0. Neglect the axial deformation. In that case, only two equations are available, and here two reaction components are there, and that's why we can say that for this number of reaction components are two, and equations available also 2, and that's why the degree of redundancy is 0. Okay. Similarly, when we consider this frame, in case of frame, we have considered the degree of static redundancy is equal to DSi external and DSi internal. Here also, we can consider external R minus E same, but for the internal, definitely for internal, in case of the frame, it is not 0, and therefore the simple equation we can use, that is here 3 times of A. A is the closed area. In case of the frame, if there are number of areas are closed, in that case we can say that the, for example, here all the areas are open, that is the frame is open, and that's why this is 0. And the reaction components in this case is here roller is there. That's why there is only one reaction. At support B, here this is the support B. Here we can say that there are three reaction. One is vertical, second is horizontal, and third is moment. That's why for the fixed end, there are three components. Here also three component, and here there is a hinge. That's why two components. And therefore, this is 2, 3, 3 plus 2, 5, plus 1, 6. That's why these are 6 and equations available are 3. And therefore, the degree of redundancy is 3. Okay. Similarly, if this frame is closed like this, in that case, the value of A is 1. And therefore, we have considered this is 3 multiplied by 1. So 1 and 6 again, these are the three external 6 components, reaction component, equation 3, that's why 3. And this is 3, 3 plus 3, we get the 6. So in this way, we can find out the degree of static redundancy. In case of the oh, now, what about the kinematic redundancy? Now, for kinematic redundancy, we have used the simple concept. The concept is very simple. That's why we have considered the slope. That means there are two translation and one is the rotation. So here, in case of the beam, we can say that the support A, there are two reaction components. Okay, so support A, two reaction components. That's why in this direction, the beam cannot move, or we can say that the support A and A cannot move in this direction and vertical also. And that's why the value of U means we can say that the translation along x-axis UA is 0. Okay. Similarly, in y direction, because of the RA, it restricts the movement along the y direction, and that's why VA is also equal to 0. But we know that the beam rotate or deflect like this. And therefore, when we draw the tangent at support A, theta A is there. And that's why theta A is there at support A. When we consider the support B, again, in vertical direction, definitely V at B, that is the in translation along the y direction is 0, but translation along x direction is there. That's why UB is there. It is not 0. UB is there because the roller move in x direction. And similarly, when we draw the tangent to this curve, we get the theta B. That's why at support B, there are two components. One is the translation along x direction and rotation about the point B at point B. And that's why these are the two. So at support B, kinematic redundancy is 2 and at support A, it is 1. Okay. Similarly, when we consider the free end, point C is the free end. Here we can see that this point can be moved in this direction. So U at C is there. This can be moved in this direction also, in vertical direction. That's why V at C is also there. And this can be moved in the downward direction. That means the rotation is also there. And therefore, there are three kinematic redundancy at C. Therefore, for the complete beam, the degree of kinematic redundancy, so DKI, is equal to, we can say that 1 at support A, 2 at support B, and 3 at support C. So it is 1 plus 2 plus 3. It is how much? 6. So the degree of redundancy at this frame is 6. So you can prepare like this. Thank you. Thank you very much.